Okay, we are live. Good morning, good afternoon, everybody. Welcome to another episode of Between Two Nerds. And today, guess what? We are going to be talking about BGP and BGP again. I'm very happy to introduce a person who doesn't really need an introduction, Petr Lapukhov, old friend, colleague, and everything else. Many hours of working together. Petr is going to be talking about how to build large data centers using BGP as a routing protocol. And without further ado, Petr, all yours.
Yeah, thank you, Jeff. Thanks for inviting me and giving me a chance to talk about my probably favorite topic, like routing in general and BGP specifically. I think today we have about, 40 minutes to go over the design that we have at Facebook. And this design, I think, has been discussed and presented before at NSDI 21. And I have a bit of a condensed version of the same talk. And I also want to have a chance to listen to your questions as we go through, maybe answer some tricky ones as if I can. So first of all, as an introduction, the BGP at Facebook has a long history. Many people work on the implementation, design, and iterations of it. I believe the first implementation was done before I joined in 2010, 2011, and then evolved to design we have today. And many people worked on the software part as well as design. This slide lists some of the names which were contributing to the paper, but many more have worked behind the scenes, and I also want to acknowledge their help as well. Okay, so let's get going. The classical flow of an NSDI paper or any academic talk is to begin with motivation. So funny enough, historically, motivation usually comes after implementation, but for now, let's pretend that we are building a system that is built to a spec or a requirement. And for Facebook, as always, people like to say the major demand for a growth of data center was the growth of a product. So here we list the few icons that reflect the products that Facebook offers, and the graph on the other side captures the growth of our FBOSS switch base that runs the BGP in data center. And as you can see, it doesn't show absolute numbers because they're confidential, but it gives you an idea that over last 24 months, we have grown like 30x in terms of the volume of deployment. This is because of just recent increase of the adoption of the switches. And naturally, the growth of a scale drives the demand for routing, scalability, and other things like reliability and a few others. Now I'll put this as a set of requirements. People often use the word scalable as the key requirement, which means, in a nutshell, it doesn't have to fail when the network is very big. And very big typically means supports over 100K endpoints. That's my definition. In reality, it's much bigger in most cases. The networks that we have to support are typically on the size of multiple thousands of devices. Obviously, the second requirement post scalability is reliability, which is a very broad term, but it means, roughly speaking, the network should not really fail too often, and support the applications that are using it. The last criteria is quite interesting. I put this as operational efficiency, which has also a very broad interpretation. It means being able to support the network with like least amount of human effort, but also being able to change things quickly if required. Typically, these two requirements are contradictory because you really don't want to change much if you want to maintain reliability or operational simplicity. But Facebook has always been, at least in the last 10 years, a highly paced culture that requires often changing things in production in a very short time frames. By the way, Jeff, feel free to ask any questions, or let me know if I'm off or not really talking things that people like to hear about.
Sure. Robert will be announcing the questions as they come.
Oh, okay. Because at the moment I feel like I'm talking to a screen, and maybe people don't even listen. That's the problem of being remote. At least in the audience, like NSDI or Nanoc, you can see if people are falling asleep or cringing, and get some feedback. Here, I just look at my slides. All right. Let's look at using BGP as a protocol. It wasn't a norm to use BGP as a routing solution for data centers. I think if you follow traditional line of thinking that was established by a few big vendors, it was always thought as data centers were L2 based, spanning tree, then DPCs. There was also branching into using OSPF or EIGRP from Cisco mostly. And then BGP was, I think, something not very popular. Despite, I think, me remembering, I think it was some white papers from Cisco many years ago about BGP, it was never thought as something we would use in data center. First time I encountered using BGP in data center was at Microsoft, where Jeff is now, which was driven by a few interesting requirements. Mostly, I think, the fact that back when nothing else used to work on multiple vendor devices. But also BGP happened to have very flexible implementation of policy and filtering mechanisms, which was one of the main reasons Facebook adopted it, because engineers at the time were very focused on controlling propagation of routes in the fabric very tightly for the goals of reliability and stability. And likely at that same time, many vendors had BGP support in their devices. And by many, you can just mention a few big ones. At that time, we had Cisco, Juniper, then was also Arista. People remember also Force10, like many years ago. Now it's Dell. Somehow they all had reasonably decent implementation of BGP, but some of them had pretty poor implementation of, say, OSPF at that time when we tried it. So BGP became a protocol of choice simply because I think it was just convenient at the time to use it. Obviously, BGP has its own challenges, right? As people explored in academia, mostly scaling limits of BGP, instabilities, and other things at the internet scale. Of course, the main source of use cases of BGP was internet routing. And there, most of the challenges were typically from things like path hunting or routing transient loops and things like this, and of course misconfigurations. Well, in data center, I wouldn't say BGP had as many problems as you would probably see in the internet, but we still had faced a few challenges in the past with convergence. More so when we wrote our own BGP implementation, which wasn't that optimized for some of the specific fault scenarios. But I think at that time, when we began using vendor implementations, the major problem we faced was the slow pace of innovation. By innovation, that means new features. If we need something, it would take a long time to close the loop and get things in production. So that last bullet point mostly led us to building our own implementation eventually. Funny enough, first one was, I believe we wrote it in 2013, was a few folks, and I was one of them. First was on Python, then there was implementation in a language called D, and the third one was in C++. So it was quite a fun ride to write BGP in a few languages and also learn in process how non-trivial it is to build a good implementation of routing stack. It's not so hard to build implementation. It's really difficult to build one which is performant and reliable. So now let's jump into favorite topic that everyone usually have, the diagrams and the topology. Facebook's topology has a specific, but in a nutshell, it's very common implementation of a clause or a fat tree. There's still lots of arguments which one is the right name for this topology, but I believe we just all call it clause. Here you see a simplified network, of course, which has the so-called spine planes, that is the interconnect multiple fabric pods. And that's the terminology that we use at Facebook. Pod is the unit of computation, or not computation, apologies, of deployment of servers. It typically has like 48 racks. And then spine plane may have a number of devices which vary from 32 to 40, not 48, 48 maximum, but typically we're never going beyond 46 because of physical space limitations in some of the locations. Nothing too, I think, radically different here from the well-established industry practices. There is all kind of tricks and fun topics that come up when you have to connect multiple campuses together, multiple locations, multiple buildings, because this is where you have to aggregate all these fabrics together. That's a whole separate story, because that layer is typically the one that experiences most pressure from the perspective of traffic demand. This topology is not fully non-blocking, of course, but nearly non-blocking above the rack switch. And in most cases, it doesn't experience much problems with the congestion or traffic demand. So this just highlights the two parts of the topology, spine and fabric pods. I already covered that. And if we go to the next slide, it shows you the mapping of BGP primitives into the previous slide. It shows you the structure of the pod and the spine. And these diagrams, which are pretty beautiful, I think the courtesy of Alexei Andreev, who was the major, I think, contributor to BGP design at Facebook, sometime before I even joined. That schematic of AS numbers is his creation. He's a big fan of BGP and its mechanics. But what these diagrams show you that BGP has a few natural mechanisms that help you map, reflect the structure of topology in BGP terminology. Here, that you can see that each pod is configuration, which is very unique. I haven't found anyone who used BGP confeds outside of Facebook. Perhaps I'm just missing something. But confeds have their own limitations, but they had some beautiful properties. Like in this case, it allows you to allocate unique ASN per device, which shows very nicely in BGP AS paths when you debug things. But most importantly, it allows you to hide the ASN structure of each pod from all the others. So from the outside of the pod, BGP confed looks like, how do you call it? Just one AS, of course, right? In this case, 65101. And if you remember the RFC for BGP confeds, you might ask immediately, well, is it supposing to use an IGP under it? And that's a bit of a kind of side topic, but this has always been a question for all these designs. How come you guys cut off IGP from BGP? Because they're supposed to be laid on top of another. Like IBGP requires, I won't say requires, it assumes IGP for some of tie breaking and loop prevention. So here, people in every company I've been to did not like the idea of having two protocols, to support in the production. So they typically trimmed down one out and then had to make BGP work without IGP. So here you can imagine that, of course, BGP has to form sessions on physical interfaces, not the loopbacks, and you may need to apply specific tricks to prevent route looping, right? Because there is no more IGP cost to break the ties across a few equal paths. And so this may create some loop conditions. In our case, we had policies that prevent route looping in these topologies and also minimize path hunting artifacts of BGP. Spine is a bit simpler. Spine devices all have the same AS number in one plane. Different planes have different AS numbers. And as you can see from spine perspective, the pods look like unique ASNs on their own, right? Then there's, of course, the upward-looking sessions from the spine, which we don't show here, but they typically use something like local AS to pretend and hide the whole fabric behind some AS number. Okay, route summarization. I in my opinion, route summarization is that thing that Facebook put a lot of efforts on. From early days, there was a big concern about the scaling limits of the hardware tables in the devices. So a lot has been done to make sure that we can summarize the state and maintain the fib size reasonable. Just mind that this work has been happening in around 2012, 2011, where the first not commercial, how is it called these days? Vendor silicon, merchant silicon devices like Trident Plus and Trident only could support, if I'm mistaken, about 8K routes in web tables. Sorry, 16K routes, IPv4 in web tables, 8K IPv6. And such was other artifacts like limit on the long prefixes in the tables. And at the same time, back in 2012-13, Facebook was moving very aggressively to IPv6 only network. And as you can imagine, IPv6 surprise requires twice more state in the fib to maintain the prefix, unless you optimize it somehow. So this was a big concern, right? And as you can also imagine, the natural point of summarization at the fabric switch. So as you leave the pod, you can summarize all prefixes into the one contiguous block. And there's also typically a few summaries, one summary for the server addresses, another summary for the rack downlinks, and so on. But this was all nicely laid out into the addressing scheme. One other thing, I believe that the RFC that myself and Fiavra worked on in the past presents a design that doesn't summarize routes. And I think there we even argue that summarization has some downsides like potential black holing, config complexity, and a few others. That's actually valid, but as always, there's 2 points of view on the same problem, and whoever wins dictates their implementation. In my experience, I learned that summarization has two trade-offs. The nice part is that summarization actually contains fault domains, right? So if there is some flapping or instability, it doesn't leak out, and this sometimes makes a difference. I only seen actually one case that made a difference, but it was a very big case where instability in the link flaps caused a whole meltdown data center. Facebook never had this problem, but we do have a challenge to support summarization through policies, as I'll describe later.
Petr, we have a question here. How do you calculate bandwidth over subscription and perhaps enforce of restriction on a per server or per application level?
Well, the easy answer is this is more of an art than science. Back when it was more art than science, you have to use some rule of thumb to roughly calculate what fits in physical limits data center. So historically, the first input was how much fabric you can put and how much devices you can pack in data center. Initially, we only had 4 uplinks per rack switch, 4 by say 40G or 100G. And that used to dictate back to the server teams how much we can place in the rack. Afterwards, we definitely evolved our modeling and we built simulation environments that can model how much traffic a rack can emit and produce and how much is acceptable to oversubscribe. Typically, our subscription ratio is at maximum 3:1 per rack switch. And that comes as a sort of a trade-off between the complexity or cost of design to lay this much fiber versus the limitation of server traffic. You have to mind that these data centers have very diverse workloads. There is some you can call computational, like data warehousing, mining the data. Disaggregated storage is a big chunk of the traffic generator. Then there's applications which serve online traffic, which is actually reasonably low traffic. But the biggest learning is that these things keep changing over years, year over year. So traffic patterns that were valid, let's say, 10 years ago have changed dramatically since those times. And the constitution of traffic has also changed. So long answer short, there is a process to calculate average expected volume of traffic per rack and then dictate the oversubscription ratio we can tolerate. But in my experience, it hasn't changed much in the last 8 years. It has always been roughly 3:1. And the only thing that changed was the speed, right? You go from 40G to 100G to 200G and next 400G of uplink speeds at the rack level.
So a bit different angle to the same question. If you look at cost bandwidth perspective today, the most optimized platform with 12.8 tera, it's 12.8. This is the only feature you can get in one RU as you progress from 3.2 because 6.4 is 2 RUs, right? At every vendor.
Right.
So,
well, okay, go ahead.
Given the amount of bandwidth available downstream to the servers, having any oversubscription, unless you do it artificially, makes actually no sense from density perspective.
Okay. Well, in our case, since you mentioned the 12.8 platform, which is Tomahawk 3, for most of this is example from Broadcom. You can split ports equal proportions, right? 16 up, 16 down. The key problem here is actually you have to be flexible on the server speed because servers come with different speed combinations. Could be 100G, 50G, 25G, and then you have uplinks. And the key is always decide how many uplinks you want in the fabric. Let's say 4, 8, or 16. 16 is almost always too much. 8 is usually the gold spot that we found working. 4 was used to be the old standard in most deployments.
So you mean it drives 8 up, 24 down ratio for you, which is 3 to 1?
Roughly, yes. So downwards, you have 32 by 200 ports, right? For example, if you look at Wedge 400 switch, I think it's public design of a Wedge 400. You have 32 QSFP 56 ports downstream, 16 QDDs up, and then you just need to pick up how many you can allocate for downstream. It could be different combinations. And this also overlaps with the whole story of what kind of NIC using the server, because we have the so-called multi-host NIC on a single server sled. Sorry, server has 4 sleds sharing one NIC. That's a whole separate story. How you connect servers to this rack switch, how do you calculate rack composition? Too many factors there.
Thank you.
Yeah, of course. So here it just shows you a summary coming out of a pod. It's all IPv6. Funny enough, it's now all IPv6 traffic with a few IPv4 addresses just used for deep injection for some services which require IPv4, like DNS, for example. Everything else is IPv6. And that IPv6 story was quite interesting. It was pushed by, I think, engineering need. We had some constraints of IPv4 address space, and we had 2 options: recover IPv4 completely or do IPv6. And about 10 years ago, was a few folks, Posab, I think, was one of them, the main person, pushing IPv6 hard as a solution. And so Facebook became a IPv6 first company. Like IPv6 is the dominant volume of traffic everywhere.
That's really great, by the way.
Oh, it was good learning. I think it was very good exercise for everything. You discover so many things that are broken in implementation of IPv6 everywhere, in kernel, in vendor, in firmware. Like, it's so much fun. Yeah, so here we get the aggregates per rack and per pod. Nothing too special, right? There's of course lots of details in implementation. So when I say nothing too special, I just try to kind of maybe simplify it. There was a lot of thinking put into how to pick up aggregates, summarize them, propagate them. A lot of art there, I would say. All right, so let's come to another important part of Facebook implementation, which is BGP policy. Facebook is one of the companies when I came, the one who used BGP policies most extensively to implement specific goals. The major one I felt was always precise control of routes and propagation, its scope of propagation, similar to like controlling the flooding domains in OSPF or ISIS, but more precisely because in BGP, since it's distance vector, I know Russ White would hate this word. People say it's path vector, but it's arguable. The major few goals are listed here, but we try to implement using policies, extensive policies. First one is control propagation. Second one, summarization. The next one, third one, maintainability, is interesting, is that using maintainability was primarily around drain and drain policies. If you remember that RFC, what I just mentioned before, it mentions operations only briefly. And when I was at Microsoft, we used to simply shut down device for maintenance, and traffic would just fail over because BGP would fail over quickly. That was a long time ago. Perhaps we have changed this practice. Facebook was always very invested into careful implementation of drain procedures for traffic moves to avoid any disruption of traffic. That was another interesting trait, I think, that the company had, focus on minimizing packet drops in the network completely to avoid any affected application. So that leads to a very careful implemented series of steps that move traffic out of device using the BGP policies. Because in the class topology, you have to do it carefully to avoid these fan-out effects or fan-in effects when ECMP group expands only partially, but you have full traffic on the device, which causes temporary congestion. So there was a special procedure for graceful expansion of ECMP groups to avoid this effect. And the last goal is, you can just rephrase it simply, is to realize the method for injection of VIP addresses, virtual addresses. The whole VIP story came from the old days when we used lots of F5s, and because this was like 2010, 11. But that stuck around because some services got used to using VIP injection. I won't say got used, kind of became a norm. For HTTP applications and load balancers, VIP injection was always the default practice. So part of the policy is being able to implement specific logic for VIP injection. For instance, being able to inject multiple VIP replicas in such a way that there is active standby copies of a VIP, or any cast VIP injection, and many others. Maybe I think it was 2 other cases. And that all was done with BGP policies. In many ways, you can think of BGP policy as a programming language to control the fabric and route propagation. And Facebook's engineers, they got very, I think, sophisticated in the policies. The policy is almost like an art, if you look at it. It's a pretty lengthy expression on each device that implements very carefully thought intent of a designer. So here's an example, I think, the most prominent of how to use policies to protect against link failures. As I mentioned, route summarization exposes you to a black hole condition, right? When a link fails and you attract traffic for a summary route, you will drop packets if there is no direct path to device. But in this topology, the path to RSW1 exists from perspective of SW1 from both through the RSW2 and RSW1 directly. So let's see what happens. When we propagate prefix from RSW1 to FSW2, we mark it as using BGP community as rec prefix. So tag here means BGP community. Then FSW2, of course, remembers this prefix, but also propagates it down to another rec switch. And to be precise, with many rec switches, it propagates it to a few of them. And it loops back to the another FSW, right? So what happens now? Now FSW1 has the same prefix learned from RSW1 with shorter path, shorter confed path, and longer confed path through this 8-looking path, like a number 8 in infinity sign. And you do have now 2 paths, primary and backup, right? And of course, it's all tagged to make it a backup path, so it doesn't repropagate again in other conditions. Because if you keep bouncing this prefix, you create a perfect condition for path hunting, which is known to cause BGP to converge pretty lengthy times sometimes. As I personally learned very painfully in the implementation of BGP that I was working on. Initially, I just did not apply any policies. But then your BGP may hunt a path for some seconds sometimes, if not like maybe tens of seconds, trying to explore all the alternatives in this mesh topology. So what happens here is that traffic going to RSW1 would prefer shortest path under normal conditions. But if a link fails, you can now bounce across via another rec switch. And we call it a backup path or a backup set, because there's multiple rec switches which can provide the same function. And of course, with a policy, you can imagine for everything, to prevent this backup prefix from leaking anywhere else, as I mentioned before, and contain the combinatorial explosion of the paths in the network. So that's an example of how you can solve path hunting with policies in a topology which is very symmetric. Unfortunately, that doesn't really work super well on the internet because their topology and graph of inter-S interaction is much more complicated, and it's more difficult to realize the same intent. So how does this help scalability? Well, I think, of course, you can imagine that since you summarize and you contain the event scope to only one pod, the events in each pod are isolated. And you can ask us, of course, well, how often these links flap? I forgot the stats. There's actually a statistic data set for that. Most of that happens from the maintenance work when people replace optics or clean fiber. In a large scale, you get these events a few times a day, if not more. I think depends on the data center. So this is not just like from faulty fiber or optics, even though faulty optics is still a source of some problems. Very often, that whole faulty optics story depends on the optics batch you get from a vendor or optics generation. Some of them could be more noisy, some not. And there's also all kinds of issues which come from the software firmware support for the optics. It's actually funny how much stuff can be triggered by bad optics. It's a whole topic of its own. Optics, it's working, optical modules, their control, management, and tuning. So many things you can learn from production once you think like that implementing your own control agent software and routing stack is everything. You just realize how much is about hardware details and the being able to support the specific platform extensions, like some controllers on the board, for example. It's just
there's one more point to that, and Petr, it's not the last time here. Hopefully, we'll go and look into details. As you see, the route is being bounced back by everyone. So you only see 4 switches here, but there are more switches. And the funny part about BGP, it has different ways to decide what the best route is when it's advertised back. It could be the oldest route. It could be the one with lowest router ID. It could be a combination of both, which you're likely to see on some Swift implementation. And depending on how they do it, there might be one switch that has no routes because it wouldn't accept routes back. It has originated as best routes. So it's a fascinating topic. I spent a couple of weeks looking into this. One of the topics we are going to cover maybe.
I think, Jeff, you and I worked on this ECMP document for BGP. The criteria for ECMP selection, which caused Linux and Microsoft, causes some grief. Interaction of best path selection algorithms on different platforms, something you don't expect. If I'm not mistaken, back when one vendor was using oldest prefix for best path selection. Another one was using router ID. And so what happened when one of them was using the oldest prefix, it would advertise different AS path than the other upstream device. And so now you have ECMP set where some of the paths have different AS path elements, same length, but different elements. And also happened that ECMP logic selection in BGP was such that if the paths are different, you would reject them, only pick up one. This was another vendor. So it caused us to trim the ECMP set dramatically because over time, the devices advertise oldest route differently, and you get a mix of AS paths. That was kind of the example of how things slowly accumulate over time, and suddenly end up in being like a big problem because now you have a ECMP set which was shrunk from say 32 to 12 elements because of these accumulating instabilities and their impact on the AS path length.
So as I said, we are going to share more information on this one. And another topic here is there's a draft in IDR working group in ITF, which we are progressing together, called the ECMP considerations, which is going to be progressing towards working group document after we get updates from Yandex, which is another very large BGP data center vendor. So if you're interested in the CMP considerations, how all the stuff beautifully works together, please go read the draft.
All right. Yeah. ECMP is fun. It sounds simple, but in reality, it's not. I was surprised how many topics you can build around ECMP only. The last topic I want to mention briefly is that protocols and their designs are quite important, and this is what network engineers find most of fun in, right? And so was I. But once we built our own BGP, we also learned the lesson of maintenance and upgrades. Typically, when you operate a vendor implementation, be it Cisco, Juniper, or whoever, you don't upgrade software that often. And you get like one ephemeral block, or maybe with support extensions and modules, but you don't upgrade it maybe weekly or bi-weekly. What we were trying to adopt, and we adopted, was initially it was even daily pushes of binaries and config changes in the early days, and then it became changing periods. But now we are started as, let's say, bi-weekly push of config changes or binary changes for the software stack, which includes routing daemons and forwarding agent. This diagram shows you the rough flow. First one, every change, be it binary or config, has to go through the emulation framework, where you just try to check for any changes in the routing state or crashes or other errors. Then there's a canary dataset, not dataset, device set in production, where you push a changed binary or a config. And then there's a deployment process which goes into the shards or scale units, where you incrementally add the new version in the fleet and see what happens. The last process is the most fascinating because very often, I won't say very often, sometimes you find issues only as you push them to like reasonably large scale. The reason being that when you push it to a small scale, the error logs aren't very well visible in the whole overall like noise of the events. And only when you push it to reasonable scale, you see the impact of a change on services or on the network. I believe this is one of the most fascinating part of the push processes in a large scale, is that some of the lessons you only learn when you push half through, and you have to roll back very quickly just because you realize apparently my push has broken something very badly, and that only became visible once I reached some scale, like say 50% of deployment. There is no process, of course, to catch up all issues despite trying. You can have testing, of course. There's always unit testing, integration testing, system tests with emulation frameworks. I think Azure, as Jeff can mention, have it's what's called CrystalNet, the framework for emulation of the network.
You cannot use this name.
No, I think it was public, if I'm not mistaken.
Not anymore.
Oh, okay. Well, it was published when I remember on the MSR website. Anyways, very company tries to build the same process. I actually admire these efforts because it's really difficult to maintain these frameworks coherently. It's not that hard to build. It takes like enough enthusiasm, but maintaining emulation frameworks robustly is quite a challenge. So this just to add that BGP policy and the rest is not everything. It's important, but then the lifecycle management of a BGP implementation is another big topic. Anyways, so this is just a final page from the presentation. It just shows that the recaps of paper. BGP allows for scalable design. No doubt, I think, maybe not necessarily because BGP is BGP, just because BGP was designed reasonably well in its time. It was well thought. It has some caveats, of course, but it's been working for 30 years now, despite some limitations. It's like Unix, has its problems, but working well. So people just keep using it. It amends itself really well to closed topology, which is another way for a fancy big tree topology with more paths. Lots of art and not say science, but optimization can be put into optimizing the policy to improve convergence and implement some specific protection logic in the network. And one, I think, the other lesson we learned that as we moved to our BGP implementation, we had to inherit all the tax and burden of supporting this implementation, which was non-trivial. You have to have a team that's, of course, available on call and does this push triaging and recovery exercises as things evolve. And I think that's it. I think that's it for my talk. This is a recap, a shorter version of a presentation we gave at NSDI. There's also a paper, I think, published at NSDI that goes into more details from the slides. So feel free to find it and read more. It doesn't, of course, discuss everything because it's nearly impossible to discuss everything about policies and the rest, but it gives you an idea of what Facebook have done to implement BGP in data centers. And I also encourage, if you folks have time, compare this to the RFC that myself and Piavs have published, because there's quite some differences in philosophies and details of implementation of BGP in data center. I can only tell that seems like there is no wrong design, of course. There's designs that you can implement and maintain. There's also a school of thought that BGP is not the only protocol that works in data center. I think Amazon was vocal that they used OSPF for the longest time, with some hiccups potentially, but they've been able to make it work reasonably well as well. So it's not just about one protocol being better than another, although you might always argue this if you like arguing about other protocols. It's more about your team's desire and coherency to support a solution, right, if you build it. And there's a big difference from supporting solution built by vendors and supporting solutions you built yourself. It's hard to tell which one is better. Both have own trade-offs. Facebook chose the way to own everything, including software and hardware. That has implications. It's been working pretty well, but definitely we learned a lot of lessons about how non-trivial it is to be a routing vendor or a vendor who builds boxes and software for them. Ahmed, thank you so much for listening. And if there's any questions, I'm glad to take those.
There are a couple of questions. I'm going to read them. And thank you so much for great and amazing presentation. So first question is whether there's a need for layer 2, and similar question whether you run BGP on RSW.
What was the first question? Sorry.
About whether you need layer 2.
Layer 2. Oh, with layer 2. So if you think about this, we have servers which are in one VLAN. So that's your layer 2. It's still switched layer 2 across the switch, but it doesn't span anywhere. We debated whether we should do point-to-point links to each server, but there's no big difference actually. But implementation-wise, it's fun because you have to support ARP and NDP on this layer 2 domain on the rack switch. But it doesn't go beyond this one VLAN on the rack switch itself. And above it, it's all BGP. So you run BGP on the rack switch as well, right? It has its own ASN. Let me see if I can click through. The most fun part, clicking through the slides and to find the right one. I want to recap this diagram. Okay, almost there. This one, right? So here, the left diagram is server pod, and you see that each rack switch, which is gray, RSW is a rack switch, has its own ASN number, which is in this case a confed number. In the RFC that has been published, this just eBGP ASNs that can be reused across the rack switches. I think in some cases you can use the same ASN across all rack switches as well, but then you have to do allow ASN, which has its own sort of trade-offs.
And there are a few more knobs actually you need to do depending on vendors.
Yeah. Oh, yeah. Or you can use like 30-bit ASNs, which unfortunately weren't available back like 10 years ago in most implementations.
Okay, so
cool.
This is clear, I believe. Next question. Petr, what is the part of modern data center routing and design do you find most interesting right now?
Part of modern routing design. Fun question. things have not changed much in routing in the last 20, 30 years. What I felt was most interesting is to exploring the topologies that use non-shortest paths. So non-closed topologies that we may have additional links and paths. And typically you may need those to build something more efficient than closed in terms of like space, power, and cost. It is highly questionable, though, whether this trade-off of added complexity for routing is worth the cost you're saving. I think there's different opinions. So we've been exploring this on the side. I don't think we have yet the conclusion whether this is the valid path to go. But I felt this was one fun part in a big scale data centers is to exploring these non-closed topologies. In web companies, you don't see things like L2 VPNs or like VXLAN or things you see more in enterprise environment. So this part is off. You just have IP fabric, and all that remains is to play with topologies. There's another part which is maybe interesting for folks. It's about simplifying config generations for the fabric. You can call it IBN, which is also an overused word. How can we manage configs and network state more efficiently? Because if you look here, it's all distributed, right? BGP config pushes its own distributed model. One topic we're still contemplating how much a centralized control can bring into this network in addition to BGP. So is there a value in adding centralized control, which we're playing with, to optimize some goals, such as rebalance traffic under link failures or compensate for inefficiencies in the traffic distribution and a few other things among others. But I would say they're more of incremental additions to the BGP and its capabilities. Probably that summarizes it pretty well.
Yeah, so you were looking at K-paths, so into topologies where there's not necessarily shortest path, but variety of them, and they're dynamic, right?
Correct. Well, you can look at, as an example, imagine you have like a link mesh between the blue switches, right? A horizontal full mesh of links, and you can bypass traffic between these devices to be able to use links of the other fabric switches more efficiently. There are, of course, other variants, but in most cases, there are nice names with topologies. If you look at HPC terminology book, but typically what results, you have some form of meshes which are horizontal, not just vertical. And then you have, as you mentioned, k-shortest paths. And there are many different ways to utilize them, both in protocol or using some form of centralized traffic engineering. Different methods. There is no universal cookbook, right, to use those.
Yeah, I would add to that. I mean, Facebook, as any other larger hyperscaler, we are intensively looking into machine learning clusters. This is where closed topology become questionable. In some cases, given high degree of synchronization and size of the flow that could easily exceed 100 gig.
This, like, if you look at the ML example, and as a public reference, we can look at Google TPU cluster, which has a torus topology. The main driver there seems to be just the power efficiency of a very high bandwidth connect. If you build a very high bandwidth network of clause, it will give you this bandwidth, but it will be pretty expensive in terms of power and space. And if you have to build many clusters, it becomes quite inefficient, right, in terms of power overhead. So this is where it could become a good space where a non-clause definitely may play better. There are other, of course, arguments against it, because anything non-clause is a bit hard to support, because the tree topology, hands down, is easy to support, right? Flows fly up and down, everything's nice. If you have non-shortest paths, you get this odd mix of flows everywhere in the fabric, and that could be a bit hard to maintain.
Yeah, I think in general, discussion about DLB, its flavors, and how it can be made work over clause is a fascinating topic and something definitely worth
for
the show.
Totally.
So, I think we are out of questions, and okay, there's one more question. Very generic one. What are data center challenges in general?
Data center challenges. It depends on the operator, right? For some of them, it could be just simply supply, build enough data centers fast enough, right? Because the demand is so high. For the others, it's just like the efficiency of utilization, right? Do you have enough cost efficiency? How much you're spending versus how much you're using. Typically for cloud companies, it's the case. Cloud companies have to be very cost cognizant to offer the best product to the customer and optimize their margins. There's also challenges of simple environment, which is one of Facebook's main goal, minimize the impact on the environment, because all these monsters, they consume lots of power. Maybe not so much as Bitcoin mining, but it's still a lot. That's in general, because data center is physical infrastructure. So you can imagine it's all about physical layer challenges. First and foremost, it's about find the footprint, connect it to the global network, and then try to operate this efficiently, right? Both power and cost-wise. Networking is, I would say, quite straightforward. Give a capacity to the applications. Still, this command didn't change. It's all about build capacity first, then operate it reliably, make sure it doesn't fail too often, and then perhaps optimize the efficiency, cost efficiency of this infrastructure to make it more company profitable. This is the three dimensions. They've always been the same, I think, in DC space.
I can concur with every word. And last question we are going to take, because we are definitely, that's going to be the last question we're going to take because of time limit.
Gotcha.
So the last question is, hi, Petr, how might this apply to a multi-tenant DC?
Multi-tenant is typically, depends on the organization. So we have cloud company. Facebook doesn't support multi-tenancy in terms of different third parties. Most commonly, what people provide is for isolation, right? And typically, isolation is done on the host in hypervisors or other equivalent by providing overlay networks. I think Azure has documentation of their virtual networks, so does Amazon VPC. That's the difference. The underlying network is a bare bone BGP IP addressing, but you realize overlays to provide separation of tenants, right? That's a whole different story. Provisioning these tenants dynamically and doing isolation is a big challenge, right? And luckily, we don't have to face it at Facebook, because we support our product in our teams, and there you don't have to do the isolation, except maybe isolation of performance. So you make sure that if you stack multiple tasks or containers on one machine, you want to make sure they don't steal CPU or network bandwidth from each other. And that I call this purely perf isolation. That problem we have to address. And that is done using mostly host capabilities, like Linux C groups to control CPU and memory isolation, and network mechanisms to control the bandwidth isolation between the containers.
And I believe this would be true for every hyperscaler. Every large data center networking today implements host-based overlays. So switching infrastructure purely provides next hop for this.
Yeah, that's, I think, the battle sort of what people tried to do this in the past by using VEPA, like VLANs to the host. That thing did not fly. Things ended up being just hypervisors or soft switches or whatnot. That battle, I think, has been settled.
Okay, thank you, Petr, so much. Would you please tell our audience how to find you, how to reach you, how to ask you a question?
Well, it's my LinkedIn profile. Usually, I sometimes check my messages there, and my email is my first name, Petr, @fb.com. I don't promise I check it every day. Facebook's communication is mostly Messenger and Workplace, but I do check my email once every few days to see if I can help anyone with a response.
Thank you. And for the reference, the RFC is RFC 7938. So I remember it off my head.
7938.
This is the BGP in large data centers. The ECMP draft called ECMP Considerations, draft Lapukhov, obviously. And it's going to be progressing. There's more and more interesting details. So, Petr, thank you so much. And I certainly hope this is not the last time you are joining us. We are looking forward to hosting you soon.
Yeah, thank you, Jeff. Thanks, everybody, for listening.